My name is María García Martínez, and this is a presentation of the results during my nearly 3 months stay at Georgia Tech as a part of the Marie Curie Research Project CoMetaS. The original planned 6 month stay was initially intended to take place at OSMET in the United Kingdom. However, it was later changed to Georgia Tech in the USA due to the fact that the work originally slated for OSMET had already been completed during another phase of the project. This change was accompanied by splitting the stay into 3 months periods. First of all, I'm going to talk a little about my curriculum, including my educational background and experience. I studied chemical engineering at the Complutense University in Madrid. Then I obtained the research proficiency diploma, which allowed me to do my PhD in the material science. I did 2 internships in Repsol company before I started working at the National Institute for Aerospace Technology. From March to June 2023, I completed a secondment at Georgia Tech, the Georgia Institute of Technology, in partnership with Polytechnic University of Madrid. These 3 months commitment allowed for a substantial contributions project goals and professional growth. During this period, I focused on working package 1, specifically task 1.2. This involved microstructural analysis of 3D printed cells with diverse parameters, encompassing factors like porosity, defects, roughness, and more. I also compare lattice design to manufacturing outcomes, reinforcing my additive manufacture characterization skills. My findings were compiled into a comprehensive report and presentation, reinforcing both project value and my communication skills. This experience had a significant impact on my career. Collaborating with Georgia Tech and the Polytechnic University of Madrid fostered lasting connection in the international scientific community. The acquired knowledge will allow me to increase my productivity in the future with a forthcoming journal paper. So, what are metamaterials? Metamaterials are also referred to as cellular materials, represent a fascinating class of porous structures that hold immense potential in engineering application. These structures, often constructed with regular lattice, use repetitive unit cells and fundamental components to create integrate 3D forms. Within these unit cell designs, struts and nodes are arranged and interconnected throughout the 3-dimensional space. It is important to note that varying unit cell designs give rise to diverse range of structural properties. The objective of my stay was to study defect analysis in the 3D printed metamaterials. Defect analysis was carried out by the scanning electron microscopy, which covered the examination of 3 types of defects within the lattice structures: webbiness, section reduction, and broken strut. A comprehensive statistical analysis was then applied to assess the population of the defects, which provided valuable information on the structural integrity of the materials. Prior to the stay, a preliminary work had to be done, which consisted in the design, the printing, and the heat treatment of the lattice structure, which we can see here. The lattice structure was designed and manufactured using laser-powered bed fusion technology at the University Polytechnic of Madrid. Then heat treated at 800 Celsius degree for 4 hours in argon atmosphere at the National Institute for Aerospace Technology. This is the list of the lattice which present various structures that we can see here. The study covered 4 different lattice geometries that we call unit cells, representing the metamaterial structures that are FCC, face centers, octet, cubic, and fluorite. And here is the photograph of the samples that I took with me to Georgia Tech. Later, during my stay at Georgia Tech, I studied the defects with the SEM. These are the SEM images showing the 4 types of unit cells. As an illustration, only one of the 4 faces is presented here, but meticulous inspection was carried out on all 4 faces. These 3 images that we can see here are examples of the result of defect inspection in the SEM. The SEM image showed defects in samples of webbiness, section reduction, and broken strut. It was also observed a general defect, the effect of the gravity on the horizontal strut that strongly affects the webbiness. Also, other general defects were observed, such as unmelted particles on the surface and the previously mentioned effect of the gravity on the horizontal struts. In this table and graph is presented the percentage of defective struts depending on the orientation. It can be seen how all defects have been observed only in the horizontal orientation. In this second table is presented the strut number in lattice depending on the orientation. Regarding webbiness defects, which are notably prevalent in the horizontal orientation, they show a more pronounced impact on lattice 2. Both lattice 1 and 2 show relatively high levels of webbiness defect, which impacts their overall structural quality. Then section reduction defects are most prominent in the horizontal orientation as well. In particular, lattice 1 stands out with the highest incidence of section reduction defects among all lattice, underlining the importance of addressing this specific defect type in this orientation. Broken strut defect only manifests in the horizontal orientation. Notably, lattice 1 shows the highest number of broken strut. As a general conclusion, strut orientations play a significant role in determining the types of and severity of the defects. For instance, all lattice present more defects in the horizontal orientation, except lattice 4. It does not have any strut in the horizontal orientation. To conclude, 4 different types of lattice structure have been designed in order to study the relationship between the defects and the 3D printing input parameters. A defect analysis study was performed by SEM to analyze the defects on the additive manufactured metamaterial structures. The defects were classified into the 3 groups: webbiness, section reduced struts, and broken struts. Other defects not included in this group was observed as the non-melted particles on the surface. The application of statistical analysis contributed to a better understanding of the combination of lattice orientation, number of strass, and defect type. Lattice orientation plays a significant role in determining the types and severity of the defects. For instance, all lattice exhibits more defects in the horizontal orientation except the lattice 4, due it does not have any strut with the horizontal orientation. To conclude, the impact of this experience on my career has been substantial. The knowledge and the skills that I acquire during this secondment will contribute to my future productivity. Some future actions are still needed. The research study paves the way for future action aimed at advancing the understanding of defect microstructure relationship and their impact on the material performance. Some compression tests in partnership with UPN are going to carry out at INTA an exploration of the microstructural features using the EBSD to correlate defects with microstructural and mechanical properties are also to be performed at INTA. Published one journal paper based on the research conducted during this period completed by future actions. To finish, I would like to thank the European Union Horizon 2020 Research Programme for the opportunity to carry out this secondment, and Professor Khalidindi for his welcome and support, and Sagar for his help, and also Daniel Barba for all the support that give us from the UPM. Thank you.